Hey everyone. So sorry I can't be there today, but we are going to be learning about the very first shortcut of derivatives that you need to know, and it's called the power rule. You've probably already figured it out. So if you have, then just bear with us as we give you some of the basics of it. And if you get a chance, you might want to check out Calculus and Musical, the power rule, to help you remember how the power rule works. But if you don't get a chance to, don't worry. I'll make sure we play it in class at some point in time. Okay, so to kind of guide us into the power rule and how it works, I want to do this warm up with you, which I don't know if that's on your handout, but if you want to just watch me do this as opposed to copying it down, that's okay too, because you've done a lot of the limit definition of the derivative by now. So we're going to start with the limit as h goes to 0 of 2 times x plus h squared minus 3 times x plus h plus 5 minus the whole entire function, 2x squared minus 3x plus 5 all over h. So a lot of stuff to do to get us to get this simplified. So I hope that you don't mind if I do some kind of shortcut steps here. So I'm going to square x plus h and multiply by 2 at the same time. So I get 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 5 minus 2x squared plus 3x minus 5 all over h. And now I can start simplifying. So my 2x squareds cancel, my 3x's cancel, my 5 cancels, and I am left with 4xh plus 2h squared minus 3h all over h. So I'm going to go ahead and cancel my h's like I have been doing in the past, and I am left with the limit as h goes to 0 of 4x plus 2h minus 3. And once you apply the limit, so h goes to 0, you're left with 4x minus 3. So this is an expression for any derivative of the function 2x squared minus 3x plus 5. So remember that the derivative stands for the slope of the tangent line or the instantaneous rate of change. And it would be helpful sometimes to have the expression for it because then you can find as many derivative values as you need. But also the derivative tells you things about the graph itself and the types of um, the type of shape that the graph takes on and where you'll have max and min. So it does a whole bunch of things for you other than just find the slope at one point, which is pretty cool on its own, but it does more than just that. So if you're looking at this 4x minus 3 and then compare it to this 2x squared, minus 3x plus 5, you may have already started to recognize that the derivative is 1 degree less than the original function. So polynomial here of x squared, my derivative is 1 degree less. Also, I'm hoping you can notice that really this term right here becomes, if you take this power and multiply it to the 2, you get 4, and then becomes 1 degree less. If you take this power here, that is 1 on this x, and you multiply it to the 3, you get a negative 3, and then it goes to 1 degree less. And then this is almost like there's an x to the 0 term here, kind of. So there is no x term, so therefore the derivative of this constant value is just 0. It goes away. So that in a nutshell is the power rule. So here is then some specific rules for different types of powers that I just kind of did 3 of them at one time there. So this power rule here is just when you have x to a power. So x squared becomes 2x. X to the 10th becomes 10x to the 9th. You know, x to the 17th becomes 17x to the 16th. And then when you have a constant out front, all you do is you take that power and you pull it out front and you multiply it to the constant. So like 3x to the 4th, its derivative would be 3 times 4 is 12x, and then 1 degree less would be x to the 3rd. So you just, again, multiply it here and then subtract 1 from the power. And then this rule here is just telling you that if you have things added together, you just take each derivative separately. So that's what I did when I was talking about it on the warm-up problem. It's like if I had x squared, that became 2x, and then the negative 3x became negative 3. Just added the derivatives together. And then this last one is the power rule for negative integers. So this actually will be used a lot when you have something written as a fraction. So let's say it's like 1 over x to the 4th. Okay, you do not take the 4, don't take the power rule here and take the 4 out front down here. You have to rewrite this as a negative power, so x to the negative 4. And then when you take the derivative of that, the negative 4 comes out front. So negative 4 x to the, and then be careful, negative 4 becomes negative 5 when you subtract. So that would be written in this form. But then you could also then write it as negative 4 over x to the 5th. So you can either understand how to go from this thing here to the final answer, or you can do these intermediate steps. Sometimes it might be helpful to have it written in the negative power form anyways. So it just kind of depends on the problem, on what the results are that we're looking for. Okay, then we have another set of rules that don't really completely follow their own, like there's not like a power rule that's quite as obvious for it. When I come back though, I'm going to actually show you these derivatives on Desmos so that you can see how they work. So the first one is the fact that derivative of e to the x is e to the x. It's its own derivative. This is not a power rule. This is the function e to the x is its own derivative. This is kind of a big deal. Like the fact that this function has itself as its derivative, that actually doesn't happen anywhere else. So that's kind of a big thing. And then the derivative of the natural log of x is 1 over x. So those are two that you just are going to kind of want to memorize. And then these are all of your 6 trig functions, which, yes, you're going to have to memorize these as well. So instead of having to use the limit definition of the derivative like we've been doing up to this point, you now have, again, what we call these shortcuts. However, there's a lot of them, right? So you have to memorize a lot of different things, but I promise you, memorizing the fact that the derivative of sine is cosine is going to be a lot better than trying to use the limit as h goes to 0 of sine of x plus h, and you have to use trig rules to figure it out. So you are going to have to memorize them. There are some things that you can use to help you out. So when I was first learning how to remember the derivatives of sine and cosine, I actually kind of think of a sketch of sine in my head to help me determine what the result's going to be. So here's the derivative, or here's the graph of sine. And I'm going to look at the slopes of the sine graph here to kind of guide me on what my result's going to be. So sine has positive slopes until it hits pi over 2, and then it goes to 0. So when I think about the graph of the derivative, I'm going to have positive values until I hit pi over 2. So at pi over 2, my graph is going to cross the x-axis and my derivative is going to go like this. Now, I promise you we're going to do a lot more with graphing of these derivatives in the future. So this is just a brief little snippet of it. And if this doesn't make sense, that's okay. You can just start memorizing these now. And then as we move forward, you'll start to see the connection between the graphs. So again, notice sine, cosine. Cosine is negative sine. Tangent is secant squared, and notice that cotangent is negative cosecant squared. Secant is secant tangent, and cosecant is negative cosecant cotangent. So all of the trig functions that begin with a C, the co-functions all have negatives in front of their derivatives, and all of the other trig functions are positive. Notice that secant and tangent have secant and tangent as their derivatives, and cotangent and cosecant to deal with cosecant and cotangent only, so they don't like flip-flop around. Okay, so then let's just do some practice. And then once we're done practicing, then you can start your homework, which I believe is a Math Excel. Okay, so first one, this is a constant. The derivative of a constant, so f prime of x, is 0. So remember, this is the slope of the tangent line, right? So a constant, that is a horizontal line, and the slope of a horizontal line is 0. So the derivative of a constant is 0. That's where that comes from. Okay, the derivative of number 2 here, just a power rule. So you're going to take each part and pull the power out front separately. So this becomes 12x to the third. 4 comes out front, multiplied to the 3. Sorry. The derivative of something to the first power is just the coefficient. So sorry. And the derivative of a constant is 0. So that's our answer. Okay. Derivative of this one doesn't happen any differently than the other ones. I did not know I was going to cough so much. 5/4 times 3 is 15/4. Subtract 1 from 5/4, and you get 1/4. 1/4. So that's the derivative of 3. Wow. Okay. 4 and 5. So 4 already has things written as one of them as a negative exponent, so we're just going to leave it like that. So this becomes 8/3 x to the third. Derivative of first degree is just the constant, so 5. And then this becomes positive 3x to the negative fourth. And since the problem started with the negative exponent, you can leave it as a negative exponent. Number 5. So I prefer to rewrite these as negative exponents and then switch them back later on. So let me actually rewrite this. Negative 3x to the negative 2 plus 4x to the negative 4. And then I'm going to take the derivative of this. So that becomes a positive 6 x to the negative 3. So be careful when you're subtracting the negatives that you don't make it a negative 1 here. And then this becomes a minus 16x to the negative 5. And since we started with things written in fraction form, we're going to rewrite it back in fraction form. So 6 over x cubed minus 16 over x to the 5th. Okay, last two, I believe. So now these I'm going to rewrite as rational exponents. So cubed root of x becomes x to the 1/3, and this the square root of x to the 7th, so that becomes x to the 7/2. So now my derivative will become 1/3 x to the negative 2/3 plus 7/2 x to the subtract 2/2, so 5/2. It's totally fine to leave these as rational exponents here, but if you need to do something else with them because of the problem and the way you're going to be working with it, you might need to go back to the radical. But that just, again, it's going to depend on the problem. And for right now, we're just going to be practicing. Okay, this one, the first thought is usually to turn that x squared into x to the negative 2, but you actually are going to be better off rewriting this as two separate fractions. So since there's just one thing in the denominator, I'm going to separate it into two fractions. And so when I separate that, that first part simplifies very nicely to just 2x. And then I'm going to rewrite x to the 1 over x squared as x to the negative 2. And now I can take the derivative of this, and it becomes 2 plus 2x to the negative 3, which again, I want to rewrite this as something in fraction form, so that becomes 2 plus 2 over x cubed. I can't remember if there's more. Oh, I think I was wrong. Oh, there was 2 more. So 8 and 9, let's finish those. And it's a good thing we switched because those are all the trig and weird functions that we need to deal with. Good news is they're actually not that bad. You just have to memorize them. So the trick to it is knowing them. You will have time in the fall also to memorize them once you get into actual calc. Okay, the derivative of e to the x is itself e to the x. The derivative of the natural log is 1 over x. The derivative of sine is cosine, and the derivative of cosine is negative sine. And this problem is goofy on its own, and there's nothing else you would need to do to that. You just leave it alone. That is a minus. Okay, now we have the last one. So the derivative of tangent is secant squared, and the derivative of cosecant is negative, so positive, cosecant cotangent. Oops. And that's it. There's nothing else you can do with that. And maybe you could simplify it with getting at common denominators and all that, but that's not what the question was asking you. So you just stop there. Okay, so that's all I have for you on this video. Go ahead and start your homework, and we will catch up on everything tomorrow.